If you want to get a really good handle on errors in your student experiment, it is a good idea to get a picture of the stock bottles. As you can see here from a survey, there is commonly about a 1% error. Sometimes it can be quite small, like 0.01, but that's quite rare. And sometimes it can be quite large. So you can see with the nitric acid, it is meant to be 70%, but it can be as low as 65%. So that works out to be about a 7% error. And so if you get a picture of those things, you'll be able to see the errors introduced from the fact that your chemicals are not what they say they are, not 100% pure. So you can see there's quite a lot of contaminants. Sometimes they're listed out. These can be quite significant, such as if you're doing in Year 12 electrolytic or galvanic reactions, you can get those certain chemicals to react first, which could be a reason why things aren't working like you say they are. The heavy metals are good catalysts, so that may interfere with your reaction, and you can see here it can be quite unique. So for the copper foil one, there's quite a lot of phosphorus, so there must be something going on in the process there that means that there's quite a lot of one type of chemical in your substance that you've asked for. So impurities are quite significant as well. Going on top of that, there's often reactions going on. And so you can see here, even when it is quite warm, you still have quite a large error there. So that's a 50% error just from the water. It could be quite crazy. It could be 7. And so you're actually getting almost nothing. So if you're thinking you're getting errors by hundreds of percent, have a look at if there's reactions going on. This one here happened with a reaction. So this one is green going to brown. We actually had a titration that didn't work at all, and we looked at the chemical and it was looking slightly brown. It should have been green. And so basically we were thinking we're getting the chemical and we're getting nothing. And same with magnesium oxide, that's quite a common one. If there's oxide layers or rusting going on. So it can be a lot more extreme than just the fact you're not getting purity. There could be massive, there could be reactions going on that give you errors of hundreds of percent. And so other issues, you can't even trust the values on the bottle. That's what they're telling you. It may actually be even less than that. And you also need to see whether the contaminants are specific to your reaction. Look for the dates when they were opened, because there's evaporation, and there's things that I'm not even aware of. So you basically need to research your chemicals as well. So just a side note, this one's quite good. It's got the person that did it, their initials when they received it. It would be more important to know when they opened it. So you need to write opened, do your initials, and the proper way to write a date is to put the month afterwards with a 3 letters, so that if you're working with other people that speak English, you might get confused, such as 1, 2. You don't know if that's the 1st of February or the 2nd of 1st of February or 2nd of January. In errors and uncertainties, sometimes I point out times where conversions and stuff like that actually can cause deaths when we're talking about large projects like NASA or so forth, mixing up dates or times or uncertainties. Okay, so that's the international proper way to write a date in science, and this is almost perfect, but not good enough. So check whether the tech is writing open received on there. That will be quite helpful to know how old the thing is. Okay, so conclusion, it's best, if you really want to get a handle of this, get pictures of the stock bottles, openings, purities, impurities, research what those things might have done to your reaction. It's even better just have a look inside, see if there's any water in there, hygroscopic, see if it's absorbed water or changed color. That would be even better. And then grab your purities and actually apply them to your uncertainty propagation. So just going above and beyond, probably not reasonable for most schools. I will take the effort if you ask, to grab the chemicals and take all those photos and put them on a file somewhere for you to look at if you're going to go that extra distance. All right, all the best.